Okay, so now we're ready to put it all together. We're back here to shining the red laser through the pair of double slits that we began with at the beginning, the first time in the first video of this series. And so you see the double slit pattern that we commented on before, where there's this spacing between bright and dark spots alternating evenly spaced. And I ended that video by saying that there was some further structure that we didn't yet know how to describe. Now we know how to describe it. Because what you notice is that that further structure is a single slit diffraction pattern as a modulation on top of the two slit interference pattern. So there's a wide, bright area in the middle here, and then a dim spot. And then you go further over, there's another dim spot, further over, another dim spot. But this wide, bright area is broken up into evenly spaced bright, dim, bright, dim, bright, dim, bright, dim. That evenly spaced bright, dim, bright, dim, bright, dim, bright, dim, that's from the two-slit interference pattern. And this wider structure with bright in the middle and then dim, that comes from the single-slit diffraction. So what we're doing here is shining the laser through two slits. Each slit by itself has a certain width. And that means that just from the single slit diffraction pattern, we should get bright in the middle, and then the first dark spot should be L times lambda divided by the width of the slit away from the middle. And then the next dim spot should be L times lambda divided by the width of the slit times 2 away from the middle. And that is this modulation that we're seeing. And the spacing between bright and dim, bright and dim, bright and dim, that's just regularly, evenly spaced. That told us the spacing between two slits. We did that last time. It worked out to about 0.3 millimeters. What you see here is that between the first dim spot to the left of the middle, coming from the single slit diffraction, and the first dim spot to the right of the middle, coming from the single slit diffraction, there are 7 bright spots. The two single slit diffraction minima are separated by 2 times L times lambda divided by the slit width. The individual bright spots from the two slit pattern are separated by 1 times L lambda divided by the spacing between the two slits. And what that tells you is that the spacing between the two slits is 7/2, so 3.5 times bigger than the width of one slit. So by studying this pattern, I can learn that the structure of what the light is shining through is two slits. And just by counting, not even by measuring with a ruler, I can tell that the spacing between the slits is 3.5 times the width of just one of the slits. And so this completes our analysis of this pattern. We now have a full understanding of all the structure in it, but it illustrates many general things. First of all, it gives you another illustration of the fact that smaller structures in the object you're shining the light on, namely the slits here, smaller structures become bigger structures on the screen. Because, of course, the width of one slit is smaller than the spacing between two slits. And the width of one slit becomes the large-scale modulation of the pattern. The spacing between two slits, which is bigger, becomes the smaller structure of the pattern. And that's very, very general. So if you want to think about how the physics of diffraction and interference are used today in cutting-edge science, imagine doing this with X-rays instead of with a red laser beam. And instead of shining those X-rays on two slits, imagine we shine those X-rays on a crystal of some organic molecule whose structure we want to learn. And this, by the way, is how the structure of DNA was first discovered, was by doing X-ray diffraction on crystallized DNA. So when you have a crystal of some complicated organic molecule, just from the crystal structure itself, the fact that the molecules are spaced regularly, you're going to get a fine-scale structure in your diffraction pattern, which is like the fine-scale structure here that comes from the spacing between two slits. And then Each individual molecule at every one of the points in the crystal has a complex structure of its own. And each of those molecules is going to make a diffraction. That means that you're going to get, in the diffraction pattern, a large-scale modulation, which is going to tell you about the structure of one molecule. So by analogy here, the large-scale modulation tells me about the structure of one slit, in this case, the width of that one slit, and the fine-scale periodic structure tells me about the spacing between the two slits. That's just like what happens in X-ray diffraction, which is how scientists right now learn the structure of newly discovered organic molecules. If you're interested in the structure of the molecules themselves, you're interested in the large-scale modulation of the X-ray diffraction pattern, and that is, in fact, what the crystallographers study.